much for this beautiful invitation. Thanks for all in the room to be here. And I'm also grateful that that the Malinka project has invited a philosopher to the discussion. I mean, it's not trivial, I'd say. It's also great that you put the philosopher at the end of the day when everyone is tired. I guess that I'm also tired, so that's why I'm sitting, also to be able to read and try to keep the time. But you know, apparently we're in France, so time is less of an issue. In any case, it's good to put the philosopher at the end of. I mean, that's what. It's just a verification I'm doing of what happened. Coming from Switzerland, for those who don't have the background where you don't really mess with these things. It's also great to put the philosopher at the end of the day, so that everyone is relaxed and you can relax with the less technical aspects, but also less focused to find the mistakes in the technical aspects that the philosopher can make. At any rate, I'll be presenting some high-level perspectives on this topic, knowing that not all of them are going to be useful to all of you, but hoping that at least everyone will find at least one of them relevant for them. By the way, the slides are on my website, so if you want to check things while I'm talking, you can find them there. So I'd like to, and by the way, the historical perspectives are not going to be there because there was not enough time. So I'd like to start by showing a 50-second excerpt of a lecture given by Tony Wu 2 years ago at the Institute for Pure and Applied Mathematics at UCLA. And for context, Wu is an AI researcher who worked at Google at the time of this talk and shortly after became a co-founder of XAI, the AI company created by Elon Musk. And in his talk, Wu is presenting his latest results at Google concerning the application of neural models to mathematics, and in particular on auto-formalization, one of the most referenced papers in that field. And he's presenting this to a very select crowd of international renowned mathematicians, including field medalists and world specialists in automated theorem proving. So I think I need to do this. There it is.
You have the first step, writing the informal proof. And in this case, we just take the human informal proof, and then we try to auto-formalize that human informal proof into a formal proof to prove that statement. And in this case, we know for sure the informal proof, the natural language proof is correct because it's generated, it's produced by a human. Okay, so we make sure that the human. So it's generated by actual, we script the solutions from the internet, like the solutions. Okay.
You're just digging yourself deeper, right?
Okay. So to me, this can be considered as one of, from a philosophical perspective, as one of the most symptomatic moments of the philosophy of mathematics in our days, and maybe of philosophy of science altogether in our days. But there are many more other symptoms in this direction, like this tweet at practically the same time by the professor of the Santa Fe Institute, Melanie Mitchell, characterizing as weird a statement made by Google about Palm, which was its latest, Google's latest large language model by then. And that that statement claimed that since the model's training data set includes many mathematical expressions, the model exhibits improved capabilities in logic and mathematics. And of course, symptoms like these have multiplied in recent years. So I guess that the first question to me, from a philosophical perspective, is what's so funny? I believe that philosophers and historians of science cannot but raise one simple but fundamental question, namely, what's so funny here? And more generally, in which way are these almost anecdotal moments epistemologically significant? And I guess that the answer wouldn't escape anyone in this specific room, but let me nevertheless make explicit a few elements of response. First, the funny thing is that proof assistants and automated theorem provers were supposed to prevent the vulnerability of human proving practices instead of reproducing them and relying on them as a gold standard. And similarly, the weird thing is that mathematical competence was supposed to be a condition to write and read scientific papers and mathematical expressions instead of being their miraculous effect, as Google is claiming. And more generally, natural language was considered the cause of the multiple problems preventing mathematics from achieving higher degrees of rigor and precision rather than the solution to this problem. And lastly, the formal nature of mathematics, assumed to be finally conquered by the logical regulation of its symbolic means, was supposed to make mathematics indifferent to the strong empirical position assumed by connectionist approaches guiding the applications of DNNs, or deep neural nets. I'm going to use DNNs all the time for deep neural nets. So what's going on? Well, as you all know, and we've seen it in Henri's presentation right before, during the last decade, we've witnessed a rapid development of applications of neural machine learning methods in the form of deep neural nets to scientific practices, and somewhat surprisingly, mathematics has not been the exception to this trend. And this despite the apparent incompatibility of the epistemological groundings on which mathematics stand. From strictly scientific perspective, results are arguably modest, although we've seen that this has progressed pretty quickly. But one can still claim that no important open question has been solved through the mathematical application of these neural models. Maybe you can say yet, if you want. However, from a philosophical perspective, the existing results are already surprising, and sometimes they are almost magical in the sense that, in a strong sense, in the sense that what these models already achieved was supposed not to be possible at all. And I don't have the time to go to give you the details of the state of the field. Fortunately, Henri has already done that work really well. But let me give you some very quick overview here. As two random examples, let me first mention these rather early results, which I will come back, or will set a little bit the running example for the whole talk, showing that GPT-3, that is a transformer model trained on uncurated data scraped from the internet, was capable, when it appeared, of performing addition and subtraction up to 3-digit with an accuracy of over 80% without any further training. And the second example is much more recent and concerns a small but tricky theorem that Sam Collis and I, John, who's sitting there, we proved for some paper relating pointwise and uniform convergence in some specific setting. And some months after that, after proving this result, John asked the latest ChatGPT by then, this was 03, I think, if the tricky part of that theorem was true, which we had already proved it was. And after 4 minutes and 41 seconds, the model came with a correct proof. And not only that, but it provided a long explicit account of the chain of thought, where it first tried to come up with a counterexample, and it gradually circumscribed the right property to show there can be counterexamples, which honestly, I don't really know what to think about it. I don't know what to do with this. I mean, should I be happy? We had a theorem, could be proved in 4 minutes. It's confirmed, right? Or not? I don't know. I still don't know what to think about this thing. Now, the way all these applications work is by appealing to the usual trick in the field of machine learning. So basically, you first define a task, then you gather data, you define an objective to be optimized, and then you pick a neural architecture, you perform a training procedure, and you evaluate the results, right? But other than that, it is difficult to say what all machine learning applications to mathematics have in common from the perspective of the philosophy and the epistemology of mathematics. And after surveying most of the works in this direction a couple of years ago, and then realizing that it's kind of a lost battle, which is, I mean, philosophers and these historians should just stop working on this until this comes down, because then as soon as you write and it's published, it's like completely outdated. But back then, and this is probably one of the reasons why I was invited here, I showed that actually the research in the field is implicitly organized in 4 groups, depending on whether the application is oriented to or toward finding mathematical proofs, manipulating mathematical objects, acquiring mathematical skills, or supporting mathematical heuristics. I'm not going to give details here. Again, Henri has done that very well. I think that an important point here is that since then the field turned very much into the reasoning and the proving part. But it's important to see that there are other ways of applying AI to math here. And actually, this somewhat imposes the fact that the practice of mathematics is plural, and it imposes it even at the heart of a very analytical way of thinking mathematics. So there's at least that for philosophers. But there's a little bit more here, which is that despite the apparent dispersion across these practices, at least that was my claim. I claimed that all applications share, even if without knowing it, a common philosophical assumption that you can already see in the symptomatic anecdotes at the beginning of this talk. Namely, the idea that whatever we do when we do mathematics, language, and in particular written natural language, plays a critical role. And the reason is that language, and more precisely writing, sorry, I'm back here, yeah. Language and more precisely writing, including the wide variety of textual forms, statements, expressions, symbols, characters, diagrams, we've been talking about all that. Writing is all these models can rely on to perform the mathematical tasks they are required to perform. So whatever happens within the black box of a neural net happens on the basis of the processing of syntax and of syntax alone. Now, of course, pure syntactical approaches exist in mathematics, and they characterize what we usually refer to as a formalist perspective. But the difference here is that all syntax, including mathematical expressions, is conceived and processed as if it were a sort of natural language, and with tools developed for the processing of natural language. And it is essential to understand that this is not a bug, but a feature of this approach. And as a consequence, the potential success of neural nets in math forces us, first philosophers, but then everyone, to revise our conception of the relation mathematics maintains with language, going as far as to revise our conception of what mathematical text is and what it means to read a text at all. More precisely, we need to understand that and how natural language, in its most immediate and unaffected expression, constitutes a decisive component of mathematical knowledge, and how and why computational practices are capable of leveraging mathematics for mathematical content from natural language expressions. So this problem has a history. I don't have the time to talk about it, but we can talk about it in the Q&A or during the whole conference in the next days if you want. So I'm going to skip that. But so I'm going to jump directly to the epistemological perspectives. And here, by focusing on mathematical practices, the history and philosophy of mathematics of the past decades has sufficiently shown already the many ways in which artificial and natural language are entangled, showing in this way how strictly analytical and foundationalist approach is not enough. To assess mathematical knowledge, one needs competence in the context, in the pragmatics, in the historiography, on institutions, on documents, on cognitive faculties, etc., etc. Now, the surprise in the face of the results of AI applications to mathematics is a symptom. The fact that we are surprised, even though the past decades in philosophy of mathematical practice have shown all this, the fact that we're still surprised is a symptom that even this is not enough. Specifically, that the surprise shows that a particular way of reconstructing or extracting content from expressions, which is original without being entirely new, seems to be missing from that count. However, the problem is that a good treatment of this problem is, at least to me, nowhere to be found in the philosophical discussion on AI. Indeed, most of the philosophical debate around AI has been organized either along the symbolic connectionist axis or, what is worse, along the stochastic parts AI consciousness axis, which, if I had to summarize it in 2 sentences, I say it features 2 opposing positions, namely the stochastic part position, holding that LLMs are not like us, and therefore they do not and cannot have any relation to natural language, and the AI consciousness, or the general AI, general artificial intelligence, AGI, position that holds that LLMs have a relation to natural language, therefore they are like us. And of course, you can find a whole spectrum of intermediary positions that believe that LLMs are somewhat like us, but also somewhat not like us. Now, it's not difficult to see that the inanity of the current state of the philosophical debate resides in the belief shared by shared by the opposing positions here, is that the epistemological problem raised by AI is that of knowing whether models are or not like us. Or if you prefer a more academic version of the same argument, that the problem of computational models of language is to be addressed in cognitive terms, which is barely more than saying that the philosophical debate has fallen into the trap of the intelligence metaphor with which these models have been branded. So there would be a lot to say about the history and the reasons, and the place in particular of Chomsky in what is known as the cognitive revolution in the 50s, but for lack of time, I prefer to focus on the specific consequence of this trap, which seems to me essential if we want to overcome the epistemological obstacle that all this represents, in particular for addressing the problem of mathematics. And that specific consequence that I want to bring up is that the cognitive bias in the study of neural models has resulted in a massive empiricist orientation in the research surrounding neural models of language. But rather than developing this point, I prefer to defer the argument to one of its promoters, Zico Coulter, who delivered one of the keynote talks in the last year's edition of iClear. And for context, iClear is one of the top machine learning AI and AI conference in the world. And Zico Coulter is a professor and director of the machine learning department within the School of Computer Science at Carnegie Mellon. Now, at a key moment of his talk, Coulter affirmed that around 2020, language modeling moved into a new era, to which he refers as the scale era, where due to the scale-oriented research driven by industry, academic research is no longer capable of building state-of-the-art models anymore and resigns finally to the fact that we won't be able to understand models from first principles. And I quote Coulter here. He said, "It seemed like we had an obvious role for academic research at this point in time. And the role was we were going to be the new scientific study of existing models. Models were things in the world to be appreciated, and we would study them. We would create the new biology or physics, or as I like to say, sometimes more like the pop psychology in practice of deep networks. And this was actually a very profitable area, a very sort of lucrative one." And this immediately tried to redeem himself and say, "I don't want to make this monetary. This is very good for research, I think." I guess at this point it's good to, end of quote. I guess at this point it's good to remember that in 2024, Coulter was appointed to the board of directors of OpenAI. So I don't know if this has been very good for research, but it has certainly been very lucrative for Coulter, right? Now, you don't need to take Coulter's word for it. It is enough to go and browse randomly the publications of any top AI, machine learning, or NLP conference during, say, the last 5 years. And you will find a huge overrepresentation of papers with titles like, "Can LLMs be an alternative to human evaluation? Do LLMs have consistent values? Can LLMs invent algorithms to improve themselves? Do LLMs know internally when they follow instructions? Do LLMs recognize your preferences?" And many, 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 many more papers like that, including papers about mathematics. So if you don't know it already, this is the state of the field. And you can trust me when I say that this is the mainstream research orientation in the field, and you can certainly believe Coulter when he says that it's pop psychology all the way down. So I'd like to argue that this cognitive bias in the study of LLMs, the empiricist approaches it grounds and legitimizes, and the consequences, or the consequent exclusive focus on models, and specifically on model performance, are epistemologically ill-formed. Because if instead of making all kinds of epistemological assumptions to characterize neural language models as brains or agents or stochastic parts or computers or models, if you suspend all speculative judgments that are ever so little beyond what you can establish in a positive way, and you consider LLMs at their face value, LLMs appear as just computable functions. But then we can ask the specific epistemological problem that computable functions raise, namely, how do you know what one of these functions does? And the point is that what a function computes, provided that this question makes sense, is not an empirical property. Functions don't happen to compute addition, as the speed of light in the vacuum happens to be roughly 3,000 meters per second, or Russian happened to invade Ukraine. And say addition as something that can be computed by a function is not an empirical object. Is not an empirical property nor an empirical operation. To compute addition means to compute it for an infinite number of cases, and that infinite number cannot take an empirical form. Now, one might be tempted to say,
is it possible to ask a question like, what you're presenting about the paper names, it's certainly true, there are many papers which is all we need as well, but how does it compare to the other domains where the self-production of mathematical papers happens, for example, medicine or, I don't know, where people rush and publish?
So the problem is not that they are publishing a lot. That's like orthogonal to the problem here. The problem is that this research is cognitive and empirical about an object that is not. That's the argument here. I don't know if that answers. It's a short answer, but that's the point here.
Yes, but I believe that there's just a social part which kind of pushes towards.
Of course, we agree on that. But epistemologically, the point here is that all this research is doing empirical work on something that is essentially non-empirical. And if we want sort of convince, if I'm able to convince you that this is not an empirical object, then one might be tempted to say it, or people who are doing empirical work might be tempted to say, and I heard these objections already, that then nothing can be done about these models. But given that we do have a formal theory of computability, addressing AI models as formal objects, as computable functions, also allows us to suggest alternative orientations where positive knowledge can be produced about these objects. So if you think of the computable function as a simple computer program characterized by some model of computation, from a formal point of view, as you all know, the classic way to understand what a problem does, as well as to obtain robust results in terms of verification, correction, optimization, and so on, is to view the program as the implementation of a formal specification defined over some abstract structure, which is often the result of formalizing properties established informally by a theory about a given content or phenomenon, right? Now, of course, everyone is by now well aware that the whole point of machine learning is precisely, there's an example there that I'm just skipping. The whole point of machine learning is precisely that for some reason you cannot, one does not or cannot have an explicit formal specification. And this is precisely where the strength of machine learning methods resides, and in particular deep learning. And in this case, the informal specification is not given in the form of a theory, but of a much more ambiguous task. But it's not that you don't have any specification, as one might be tempted to say. The specification is there, it's just given implicitly in the form of data, in a way that the best that you can do is to find a function that performs the task well enough. So I don't need to remind the advantages of this procedure, but the key point is that the empiricity is not a matter of the function, but of the data. What is empirical, at least in part, is the data, not the function. So if you want to study something empirically, it's not the model or the function that you need to study, but rather the data. Any empirical analysis of the function itself is entirely besides the point. And in the face of it, both a practically exclusive focus on the model or the program or the function itself, and the practically exclusive use of empirical methods, let alone the cognitive bias, appear as what they are, epistemological obstacles that need to be removed. So for a computable function, the only legitimate epistemological question is, what is this function the implementation of? Now, does that mean that we need to throw away any data-based approach to computational model? And the whole point of this talk is to answer no, because a different research program is suggested at the crossroads of these two orientations. Namely, should it be possible to make explicit the specification that is implicitly given in the data in the form of a formal structure? And if that were possible, then unlike current empirical evaluation interpretability practices in the field, we could use that inferred structure as a formal specification, which can both provide theoretical insights with respect to the under-specified task and formal explanations with respect to the computable function. So in this way, at least two main tasks lie before us. we should be able to account for why and how, independently of the model, a phenomenon under study can be captured through the distributional analysis of data at all. I mean, this might not be true for any phenomenon. Let's say giving loans to people. Maybe that's not something that accepts to be computed out of data. Maybe that's a moral question or a political one. So the phenomenon in itself needs to be, before any model, capable of receiving an empirical or distributional treatment. And the second question is, we should be able to determine what the general principles are for capturing distributional phenomena. Okay, so let's try to move to some elements for discussing these two steps. So once you refuse to be impressed by cognitive metaphors and see AI models for what they are, namely computable functions whose formal specification is given only implicitly through data, how to interpret the fact that from purely linguistic data, a model is capable of, say, performing arithmetical operations with an accuracy that is significantly above random. This is still, I mean, and you don't need to look at the models right now, which, by the way, I showed that model, GPT-3, and it was addition up to 2 or 3 digits. Now they are at 8 digits or whatever. But you just can't, the philosophical problem is already there with 2 and 3. So how is that even possible at all? Without even thinking about the model, right? In this respect, the only plausible theoretical principle out there, at least the one that I could find, that looks like the beginning of an answer to this question is what goes by the name of the distributional hypothesis, namely the idea that important aspects of the content of a linguistic unit are highly determined, not by reference, ideas, intentions, or concepts, but by the distribution of the units over a corpus. That is, the relation to the other units in the context of that corpus. Another way, more direct way of saying this, I can borrow that from Rubinstein, and I'm good enough to say that words which are similar in meaning occur in similar contexts. So if you analyze the context, then you can have something about the similarity of meaning of words. And this idea is far from being new. It goes back to the work of Harris and Zelig Harris, the linguist, and even further back to Saussure and the structuralist revolution in linguistics during the first half of the 20th century. But current neural approaches to natural language seem, therefore, to be a continuation of this theoretical tradition. One could even say, even against classical Chomskyan approaches. However, neural approaches don't just repeat this theoretical stance, but also renew it in many ways, in particular by a computational implementation of the distributionalism through word vector representations or word embeddings. And I will return to word embeddings in the last part of my talk, but for now I just want to mention that there has been a proliferating amount of effort in the field to develop an understanding of these embedding spaces, but some of this work is extremely interesting, and there is some work in particular for the mathematical embeddings, and I cannot recommend enough the work of François Charton, who has been mentioned by Henri before. So if there's a place to start, that I would say that's it. But most of the work in this direction, especially in the last 5 years, suffers from the model-centered and empiricist bias that I mentioned before. So picking up on the first of the 2 research tasks mentioned earlier, the challenge is that of developing a purely distributional approach to mathematical content. In other words, we need to figure out how mathematical content can be encoded in mathematical expressions, and more generally, linguistic expressions, not only mathematical ones, in such a way that the distributional analysis of a sufficiently large collection of those expressions is capable of recovering it. In other words, the question is not how a model can do it, but how such a thing can be done at all. Now, from a strictly distributional perspective, and the principles that might characterize the semantic effects that we can expect from it, mathematical objects can appear vastly different from those with which we have become familiar. So take, for instance, and this again will be my running example, which is pretty disappointing if you're thinking about mathematics in general, but take the seemingly simple case of natural numbers. So the mathematical content of numerical expressions, let's say numerals, or more specifically decimal numerals, and when I say the content of it, one can think of infinity, discreteness, the recursiveness, ordinality, cardinality, constructiveness, you name it. Any content that is attributed to the set of natural numbers. All those contents are largely thought to be governed by a set of rules typically given in a different expressive system, such as a system of axioms like piano axioms, which provide an explicit account of the syntactic constraints given the semantics of basically 0 and the successor function. And certainly, one can have a purely syntactic approach to this other system, but the originality and the challenge of a distributional perspective is that of characterizing the content of expressions at the very level of the syntactic properties of the same expressions that express that content, not of a different system. In other words, the question is how to go from numerals to numbers, to borrow Dirk Schlimm's beautiful expression, without relying on a different set of expressions that governs that syntax. So how could you characterize, for instance, the recursive structure and the total order of the set of integers if you were only given a corpus of raw linguistic data? And at this point, I need to make a disclaimer. I need to warn you that what I'm just about to say will be highly speculative, which is just a philosophical way of saying that my remarks are even less than hand-wavy. The goal at this point is not to rigorously provide a solution, but to modestly delineate the area of a problem. Using an expression that Jean Petitot borrowed from Daniel Sibony, I'd like to say, though, that it may happen that our ignorance is great enough for this to be useful anyway. Hopefully, you'll see the feeling of hand-waviness fade away in the last part of the talk. So first of all, if you're given a linguistic corpus, you cannot assume numerals exist, right? Since they don't constitute an immediately recognizable and coherent set. And adopting a naive distributional perspective where a similarity of words can be established through the similarity of their context, that won't help because a great variety of strings share similar context with the numerals. Think, for instance, of the number words, right? However, if instead of words you consider characters, and their left or right first character context, then a pretty robust pattern emerges from the distributional analysis. Namely, you'll see that digits, that is one character numerals, that's how I'm going to use the word digit, just one character numerals, and numerals a string of digits. You'll see that digits have a very similar distributional profile. And this is an illustration that you can take from the pointwise mutual information between pairs of consecutive characters for the 40 most frequent characters in some version of English Wikipedia. And not only you can visually recognize the similar distributional profile of digits, the row vectors look alike for digits, right? But different kinds of clustering would consistently yield a cluster for digits in a rather stable way. Now, how do you go from digits to numerals? And in particular, how do you go in a way that something like a recursive principle is involved, only through distributional properties? And I don't have an answer to this question, but let me wave hands in the direction of two possible principles involved in the action of a recursive structure at the level of the character distributions. So the first one, something that you can already sort of visually see there, if you order the rows and columns through this hierarchical clustering. Basically, the intuition is that digits follow digits. So if you're in this matrix here, you can see that you obtain roughly a block diagonal matrix, which suggests that if you conceive this matrix as some sort of map, computing the next token, and I mean, we've heard so much that that's what neural nets do, right? If you are computing the next token, and this is a map, this matrix can be seen as a map doing that, then that map can be seen as a direct sum of two maps, one of which is always concatenating digits, right? And this is just out of distributional properties. The other principle, you can see it more if you just take the positive values there, right? It's sort of a diagonal block matrix. And you can see it even clearly if you just take the centroid of any cluster in rows and columns, and there you can clearly see that digits follow digits, and it's the only class that does that. But there's also this thing that if I weigh in the pairs of digits, they also have the same distributional profile, as I say. So if you do a clustering there, the pairs of digits are going, the digits concatenated, at least to the length 2, are going to be clustered together. So I feel that like these two principles could be combined to characterize the numerals as the free monoid over digits, that is, as the closure of the class of digits under concatenation. Now, this is strictly speculative. I don't have any proof of any kind of that, but you can sense that something could be looked for in that direction. My point is that if that is possible, what you see there, it's extremely different to and much more difficult as a characterization than appealing to the successor function, for example, to characterize the numbers. In particular, it might happen that you can only characterize numbers up to a maximum string length, after which your data is too sparse to guarantee anything without further inductive bias. And indeed, LLMs struggle to generalize outside some fixed string length. However, the existence of a distributional property or distributional properties of digits under concatenation, as the one that I mentioned, might suggest that extracting relevant recursive principles from data is not altogether impossible. And this is independent of the model. Now, the possibility of recognizing the class of all numerals among all characters strings is certainly not enough to characterize the class, that class as a class of integer, even if such a class is determined by a recursive procedure potentially learnable from linguistic data under some sort of inductive bias that would be compatible with neural nets. After all, following classical Chomsky analysis, any natural language is characterized by recursive procedures, right? However, unlike other possible formal languages, integers have the specific semantic property of being totally ordered. And at first sight, it is difficult to see how distributional properties could provide any means to account for such an order. At most, one could use length of strings, but nothing could be said about whether 24 and 42 are greater or smaller than each other, right? However, as I'm sure some of you know here, somewhat unintuitively, leading digits in naturally occurring numbers in empirical corpora are not uniformly distributed, but follow a particular logarithmic law known as Benford's law. And in particular, the leading digit of numerals from 1 to 9 in empirical data roughly distributes around the logarithm in base 10 of 1 plus 1 over n. And there are many explanations of this, but relatively recent interpretations show a link between this curious fact and positional writing in some base. Now, what is important for us is that if we order our set of digits following their probabilities, which is clearly a distributional property, we can expect our digits to be ordered following their numerical values, seemingly recovering in this way a semantic property. But of course, what looks like a curious fact from the point of view of someone who already knows the semantics of numerals is totally trivial from a formal perspective, because I can order any class of characters by their probability, and that doesn't invest those characters with a numerical content. So for this curious fact to be formally significant, the order should be compatible with the recursive principle characterizing the class of all numerals, namely with concatenation. In other words, when I concatenate two different pairs of digits, one would like that their respective probabilities can be computed out of the probabilities of their respective components and reflects the order of the numerical values. In other words, we are looking for a function that satisfies the condition that you have there. So I'm running out of time, and so I'm not going to go into through the details, but we can show that this function exists just because we can invert, basically we can invert Benford's law. And Benford's law generalizes to numbers of more than one digit, and you can use the decomposition by the base on the numerical value and invert that. So that function exists. And if it exists, it's a function over probabilities, and in principle, statistical model would be able to capture it. The whole point is, would Benford's law show in the data? And again, running out of time, the short answer is it's not obvious, but if you do some work, actually you can show that if you filter for dates in Wikipedia, basically you have it not only for the first values, but also for the 2 digits. And then again, you can imagine how this function is compatible with concatenation. Right? Now, I really don't have much time, probably 10 minutes if I'm sticking to the 50 that you mentioned. 7 or 10, 12. We're fine. Oh, fantastic. 20 minutes, that's fantastic. With questions inside. We're cool, that's fine. I'm happy with that. So I can go into. Okay, I thought I'd started at 5. Okay, good. So that's good because what I'm going to tell is the thing I'm most excited about. And if you have questions about this other part, we can discuss it during the Q&A. But so as I said, all this does not have any other intention than delineating a problem and providing a conceptual perspective, but it remains extraordinarily hand-wavy from a formal viewpoint. And the only goal, I insist, of these remarks is to try to convince you that a distributional approach to mathematical objects is at once unlike any familiar foundational approach that we know, and not entirely impossible, even if that possibility is full of dangers and the devil is really in the details. So if we want to give a chance to this possibility, we need a more rigorous way to approach distributional properties of data, which could be both used to account for how content, including mathematical content, can be formally characterized from syntactic data. And we can also have some explanatory value with respect to actual models. So in the remaining part of the talk, I'd like to present briefly the main lines of a work in this direction, in this more general direction. It's not about math. And this is a work that I've been doing in collaboration mainly with John Torilla, who's sitting there, and Thomas Eiler, who might be known by many of you, he's going to be here tomorrow, but also Luc Pellissier, also sitting there, Samantha Jarvis, Titan A. Bradley. You're going to see a picture of them at the end of the talk. So let's come back to the actual distribution models. And as most of you know, I'm sure current LLMs are often composed of 3 relatively independent programs executed sequentially. So first of all, you have the inputs are automatically divided into subwords, subword units or tokens by a tokenization program. Next, each of these units is transformed into a vector in such a way that the resulting vector space is taken to implicitly encode significant linguistic properties of these units. And these are the word vectors, vector representations that I was talking about before, or the embeddings. And finally, each one of these vectors in a sentence is combined with all the others to produce word vectors that are sensitive to the context of that sentence. And this is done using a mechanism, as you all know, called attention. So I'd like to focus on the embedding mechanism here, which is arguably holds the key to the entire pipeline and represents the paradigmatic form of the distributional approach in the framework of language models. So the bet is that once you understand the embedding space, then you can understand tokenization and attention with respect to that. So how do you get one embedding function or program? And the usual way in which this is done is known to everyone. Basically, you gather a ton of junk data and you turn the neural net crank. That's how you get your embeddings, right? And at the other end of the neural net, you recover an embedding model that is a computable function or a program which outputs a vector for every word or token in the input. And these vectors have surprising properties. I'm not going to comment on them. I'm sure most of you know them. And also, as you certainly know, Word2Vec is the best known of these models from 2013-14, but they are still used across the board, even if many other things have appeared since. Now, to make things easier to grasp, I will stick to my rhyming toy example of characters in the English Wikipedia. From a strictly formal point of view, there's practically no difference. So an embedding model trained on data will take a character and output a corresponding character embedding that is a vector representing that character. And if I could zoom there, you would see, in this case, after training, that Word2Vec models in this model, character embeddings cluster more or less into digits, vowels, and consonants, right? What is important is that we are here in the presence of a clear case of what I have presented right before, which lies at the heart of language models, right? And indeed, to understand the embedding space, a lot of empirical work has been done to try and check things there. So how can we do otherwise? If you trust me that this is ill-formed epistemologically, just go into the embedding space and try to find something, right? So to start answering this question, I'd like to draw your attention to what I consider a fundamental result that appeared right after the release of Word2Vec, so more than 10 years ago, which in my view hasn't received the attention it deserves. In 2014, Levy and Goldberg proved, not by empirical method, but by a formal analysis of the cost function, that what Word2Vec was doing is to perform an implicit low-dimensional factorization of a point-wise mutual information word context matrix. And what is more, they recall that the algebraic technique of singular value decomposition, or SVD, provides an exact solution to this problem. So to me, this is the first fundamental step towards moving away from a model, and towards data and finding principles to characterize its underlying structure. Principles that can be mobilized to formally explain the behavior of the program through data, as I proposed before. However, the idea has barely been pushed in the field, and in particular, the authors of this result recognize that they didn't know why this alternative approach worked. And they asked, can we make this intuition more precise? We'd really like to see something more formal. And as I said, it's been more than 10 years from these results, and we have hardly seen anything in this direction. So this is where the work we are doing starts. So what would something more formal look like? So take the Wikipedia corpus, again, and the matrix. And a matrix can be interpreted in many ways, as you know better than me. But one of those ways is that a matrix represents a function or a map from the product of two sets, in this case it's x and y, of terms and context, to the real numbers, right? Now, if you have such a function, you can reorganize it in two ways. First, you can carry that function, right? You can see it as a function from characters to functions over context by simple carrying. And I can also see it as a function from context to functions over characters. So if you give me a context, I give you a column vector. While in the first case, if you give me a term, I give you a row vector. So you can see that, you can diagrammatize that in this way. Now, I can also extend linearly the set of characters and embed them, or embed that set in the set of functions over characters, and do the same with the set of context. And since this extension is free, then the maps that I had before can be lifted to maps between functions over characters and functions over context, and vice versa, which are the ones that are represented there as m upper star and m lower star. Now, I can compose those maps and obtain this way two operators, one from the set of functions over characters into itself, and analogously for the other space. And it turns out that these operators have a lot of structures, a lot of structural properties, sorry. In particular, if you're working over the reals, you can apply the spectral theorem and obtain a set of eigenvectors for each operator. And these are the vectors precisely by which you construct SVD. So when you perform SVD on a word context matrix from a formal perspective, what you are doing is constructing a covariance matrix And of either words or of context, and then taking the eigenvectors of those matrices. So if you apply your operator to your space, you will see that most points will be moved to other spaces, to other places of the space. But some points will be fixed or moving along some fixed direction. And it turns out that if you inspect those particular points, in the case of the operator constructed from the data of linguistic context, these points have a lot of structure, or reveal a lot of structure in the space. In particular, you have an order of importance, and the eigenvectors are paired, left and right. But also, at least in this case, they are highly interpretable. So here you see the three most important eigenvectors, or singular vectors if you want, the left one. And there you see that it distinguishes between digits and letters, and the second one distinguishes between vowels and consonants, and the third one identifies the special characters. And you have similar structures for the case of words. So just to finish very quickly, I'm not going to give the details, but I'm going to just give you the idea. The whole point is that this whole analysis of what lies behind the actual objects that the, let's say, classical neural nets are trying to get, because they are optimizing that objective. If you take all this formal analysis, you can have a categorical generalization of it, or let's say a categorical version of it. And instead of having a matrix, you will have a profunctor, meaning a functor between the product of two arbitrary categories, say two discrete categories, into some enriching category. And I'm going to jump on this, but basically it's the same story. There's a paper that is referred in the slides. You can go and see the details there. But basically, you can still construct these operators on the respective characters, and you can ask for their fixed points, and then you can consider the set of fixed points, right? And these are the analogous to the eigenvectors that we had before. And the whole point is that before, you only have a set of fixed points whose structure is just, it's an order set. That's basically it. Well, you have a pairing. It's an order set over a pair of, so it's an order paired, if you want. It's a set of ordered pairs. In this case, because of the way it's constructed, much more structure can appear because of the categorical construction. And so if you take as the base case not the reals, but the Booleans, basically you put a 1 or a 0 if two things can go together or not in the corpus. So basically you discretize your original matrix. And then you have this categorical approach. You construct your operators. You identify the fixed points. Then these fixed points, the ones that we're distinguishing, let's say letters and digits before or things like that, these are the ones that you get. And you can interpret them as subsets because they are Boolean vectors, right? But subsets have more structure than the vectors that we had before. You can use inclusion between subsets. And that tells you that the set of fixed points now has a much richer structure than just being ordered. And so weirdly, by moving from the reals to the Booleans, we seem to be losing something. But actually, in this categorical setting, we see that this is gaining you some structure. So one would like, of course, to have the best of both worlds. And one would like to enrich this setting not with the Booleans, but with the reals. And that's actually what we are doing. Situation is the same. You have a set of points. Go through the operators. You pass them through the operators. You get a set of fixed points, which is the one that you have in the left. You have a better picture there. And then you try to analyze that structure. And that structure, hopefully, is going to tell you something important from the point of view of the structure of the data that we are analyzing. So I'm going to stop here. Maybe just one last comment is that this is a fresh theorem that should be on archive in a month, let's say. I'm looking at John because he's responsible for this. But it's possible to prove that, in particular in the case of the reals, every point in the nucleus, in the set of fixed points, is formally equivalent to a type defined as in a linear logic way as a closure under or a biorthogonality. So it's possible to extract from this structure a type system and hence an explicit formal logic, which will then be connected directly to the data that you're analyzing. So thank you very much. Sorry for being too long. And here are the takeaways, which is just a repetition of what I've just said.